Okay, so this in the lab, this will be your experimental spectrum. This is carbon monoxide. Isn't it beautiful? Look how clean it is. Those different spectral lines are the rotational lines. And since it's a diatomic, it only has one stretch. And so by definition, the stretching has to be along the symmetry axis. And so we lose the delta J equals 0 selection rule. We can't have that Q branch. And so there's a missing Q branch in this one. Diatomics, by definition, cannot have a Q branch because all of their vibrations are along the symmetry axis. We have, if you look at the x-axis, that's the transition energy and wavelength, wave number, and the lower energy side is the P branch, and the higher energy side is the R branch. And so anytime you see rotational spectra like this, Rovibrational spectra, always look to see if, how the data is plotted. If it's plotted with high wave numbers on the right, then the Q branch is on the right, the R branch is on the right. And if it's reversed like this, sometimes in infrared spectra we plot it in reverse, then the high wave number values are on the left, and that means the R branch is on the left. Okay. Now we're looking at this, and what we want to do is, let's see, where's my assignment? Okay, so it's coming up. All right, so what we're going to do is we're going to use this spectrum, and we're going to label those peaks, and we're going to analyze those and get the B value. And so once I have the B value, what do I do with it? And so let me kind of show you where we're going with it before we do the assignment of the spectrum. So here's a sample calculation. Once I've calculated B, what do I do? Well, this is the rotational constant. And we're starting with the simplest molecule. It's a diatomic. And so it'd be nice to give you guys a more complicated molecule, but let's start with baby steps, right? Let's just deal with two atoms bonded to each other. So we have one structural parameter in this molecule, that is the bond length. And this is where it is in the rotational constant. It's down here. This is the bond length of the carbon monoxide molecule. And the spectrum gives us this B value. So we get that from the spectrum, and now we can solve for their bond length. Now here's the calculation. Look at all those units. And this is why you struggle with the PChem calculations, isn't it? Because there's all of these units and all of these constants. And a lot of times people just leave the units off. And if you leave the units off, you'll miss these kinds of things where you have to convert from grams to kilograms. Or if you use your masses in grams per mole, then you've got to use Avogadro's number. Avogadro's number is nowhere in this equation. But if you're using mass in grams per mole, you've got to use it to get rid of that per mole. If you're using grams and Planck's constant, you've got to get out of grams and into kilograms, or vice versa. So this is typically your problem in PChem is not following the units because you don't include them in your calculation. Okay, so if you would be sure to write out all your units, then you'll know when you have to do these conversions. Well, this whole piece up here doesn't change. And so make life easy for yourself and calculate this one time and make it into a constant. You can consolidate all of these things and you can make this constant, and that is note card bait, right? Because all of this stuff, Planck's constant, Avogadro's number, conversion from angstroms to meters, kilograms to grams, the speed of light, 8 times pi squared, put all of that into one number that has the units. So all of these units cancel except for a few things. The kilograms are canceling and meters squared are canceling here. And we've got some seconds per seconds here and the speed of light. And we've got, let's see, the centimeters in the denominator is going to give us wave numbers for our B value. So we're going to leave that alone. The per mole from our masses is going to cancel with this Avogadro's number. Actually, yeah, we're going to leave that in our calculation because we're going to use this one here. So I'm going to not cancel that. So anyway, all of these cancel out to give us in the upper constant angstrom squared per mole per centimeter and grams. So grams per mole. So that constant has the units grams per mole, angstrom squared, wave numbers. You see that? And then that's going to cancel with our mass in grams per mole, our bond length in angstroms squared, and it's going to give us wave numbers for B. Pretty straightforward. Now, it's important, if you're going to do this, to use all of the significant figures that you find in NIST. And I had that on a front slide of one of the earlier sets of notes. And that way you don't introduce rounding errors into your constant. So if you're going to make a new constant, make sure you use all the sig figs of all the constants that we have available. And whenever you're doing your lab calculations, use all of those so that you have good results. So let's solve for the bond length of fluorine. So this is a typical problem. You have an S branch line in the Raman spectrum of fluorine, and they are 3.56 wave numbers apart. What's the bond length? That's enough. Just measuring those two spectral lines and taking the difference is enough for us to solve for the bond length of fluorine. So we go to the periodic table and we see that F2 is 38 grams per mole, so 19 apiece, and therefore we can calculate the reduced mass. So the reduced mass over here is M1 times M2 divided by M1 plus M2. If it's a homonuclear diatomic, M1 equals M2, so you have M1 squared over 2 M1, and essentially the 2 M1, you could cancel one of the M1s, and you end up with M1 over 2. So for a homonuclear diatomic, it's just half the mass that's of the molecule. Okay. And so then we end up with this constant that we made up. We have the grams per mole, and this is what I'm talking about right here. That's the difference in the spectral lines, and we divide by 4. See, there's no unit associated with that. You just have to know, because it's a Raman spectrum, that the difference between those peaks should be divided by 4. So that's illustrating the importance of this thing that I'm emphasizing with Hamlet and everything like that. You've got to know what kind of spectrum you're doing, because you'd never catch that error if you don't know what kind of spectra you're dealing with. And so we end up with 1.41 angstroms, so that's fantastic. Piece of cake calculation once you get B, and you can't get B without knowing the 2B or 4B thing in the Raman or IR. Okay, so now let's look at your carbon monoxide lab. This is your spectrum, and you're going to label those peaks. This is where we get into peak picking. So you pick each peak and you assign quantum numbers to that transition. So we have the P branch on the low frequency side, the R branch on the high frequency side. So that's your first assignment, is to think about which side of this spectrum is the R and the P branch. Then you go to the middle, and that first line to the low wavelength side or low energy side of this gap is the P1 line. And the one above it, above that gap, is the R0. So that's where you start. You start in the middle, and then you work your way out. So going down the P branch, the next one's the P2, then the P3. And so let's think about what this means. We're on the P branch side. That means delta J is -1 here, okay? And so for this right here, let's look at the vibrational transitions. This is V double prime equals 0 to V prime equals 1. So it's a fundamental vibrational transition. J double prime is equal to 3 to J prime equals what? What are we doing here for the P branch side? We're going down, and so J prime should be 2. Going down by 1 J level. So that right there is what's happening for that peak, the P3. So every peak has a connection of 2 different quantum numbers in the upper state and the lower state. And you can see it just keeps going up, 4 or 5. You just go all the way as high as you can go, 25, 26, 27. If you can get to 27, that's great, okay? It starts to get down into the noise. And so if you start picking noise peaks, you're gonna harm your precision. So, but you want to get the higher quantum number peak, because that tells you more about like centrifugal distortion and so on. As the molecule spins faster and faster, the bond length stretches. And since the bond length stretches, the B value changes. and it's a function of the quantum number cubed. And so getting one more peak out of that adds an incredible number to that analysis of that centrifugal distortion. So you want to get as many peaks as possible so that you can get good statistics on that centrifugal distortion. We're actually measuring how much the bond length stretches as this molecule spins, which is pretty cool. Okay. Then we go down the R branch side. R1 is next, R2, R3. Let's go ahead and do this for R3. We have, again, V double prime equals 0 to V prime equals 1. That's the same for all of these. But this one is going to be J double prime equals 3. Notice these are labeled by those lower states. To J prime equals what? For the R branch, it's plus 1. And so it's going to 4. See what's happening? Yeah. Okay. And then we have R4, 5, 6, 7, all the way up. And here we're actually running into the carbon dioxide spectrum. So it gets confusing. These peaks are from carbon dioxide. And so you kind of get into a forest of peaks over there, and you got to make sure that you're looking at the ones that are decreasing and getting closer to the noise. Yes?
You may have said it, but why do the R values start at 0 and the P values start at 1?
Yeah, excellent. And so this one here, P1, is because delta J has to be -1, and we can't go less than 1. So if we started at P0, we'd have to go to J prime equals -1, and we can't do that. So that's it. But we can go up. So we can start at R0 and go up. We can't start at P at 0 and go down to -1. That's it. So that's very important. Now this, what is this M thing? Well, think about this. We have 27 or so peaks on either side, and the difference between each one of those peaks is 2B. So how would we calculate B, right? We have, what do? Take the differences between each of these peaks and come up with 27 measurements of B on one side and 27 measurements of B, and then take those 52 measurements and average them. That's one way to do it, okay? But what you're doing by taking all of those differences and averaging is what's called a linear regression. So we can let Excel do that, and it's a lot faster. So we could do a linear regression on the P peaks, on the P branch, and get a B plus or minus some really good statistics. And then we could do a linear regression on the R branch side and get B values with some really good statistics. But now we have two determinations of B, one from the P branch, one from the R branch. Which one's right? They're going to be different numbers. Do we then average those? What do we do with the statistics then, the uncertainties? And so it would be nice if we could get one regression for the whole thing, both the P and the R branches. And so we come up with this fake quantum number. I'm going to put there fake. Okay. Okay. We're just going to define this M quantum number, and we're going to run it from the P branch all the way into the R branch. And so we're going to say for the P branch, M is equal to minus J, and for the R branch, it's J plus 1. And so down here, we can have this fake quantum number, and now we have negative and positive values and a 0 in the middle, and we can do a linear regression with respect to M, and we will get one B value for the whole spectrum, okay? But I call it fake because it looks confusing. We have negative quantum numbers and so on. And I've just said we can't have a P0 because we can't go to J equals values less than 1. So this is a fake quantum number. We call it a running quantum number, and it runs through both branches. And so this is how you define it. You have that P1 is minus 1, and the R0 is plus 1. And so when this M quantum number crosses 0, that is the vibrational frequency right in the middle. Okay. And so there's a handout that goes with this lab that's pretty long, but I want you to read it. It's from this book, Experiments in Physical Chemistry by my old professor, Joseph Nibbler at Oregon State. And he comes up with these equations, and then he introduces the running quantum number M, and he has M down here, this is that using that fake quantum number, and he has these other terms here. This dE is the centrifugal distortion constant. So that's how much the bond stretches as it's rotating faster and faster. It has this alpha E, which is a new term for you. That's the rotation vibration coupling constant. So have you ever seen a figure skater spin and then they pull their arms in and they go faster? Okay, if this bond is stretching, when the bond shrinks, it'll spin faster. And when it stretches, it'll spin slower. And so doing it like this, it's slow with a long bond length and fast with a short bond length. And so it's doing this. And there's a constant associated with that. And that's alpha E. So it's the vibration rotation coupling constant. And we can determine that from these regressions. And then we get our B values. What I don't like about this equation is this piece right here. My constants are like combined together in front of that M value. So I'm going to rearrange this equation, and I'm going to say, don't use Nibbler's equation, use mine, okay? Because what this allows us to do is we can create a linear regression with columns 1, 2, and 3. And so we're going to assign our J values, our P values, our R values, and the J values. And then we're going to use those definitions that M is minus J for the P branch and J plus 1 for the R branch. And so we're going to have a column of M values for every frequency in the spectrum. And then we're going to take those M values, and in another column, we're going to multiply them by 2. And so that's going to be column 1 is 2 times the M value. Column 2 is going to be this crazy thing. It's going to be minus 2M minus M squared. That's going to be the formula you put into column 2. And then this is the formula you put into column 3, minus 4 times M cubed. If you'll do that, and then you do a regression on these 3 columns, notice the coefficients of those columns. This coefficient is just dE by itself. This is alpha E by itself, and this is BE by itself. So the regression output will give you these 4 values. And you'll have the vibrational frequency, the rotational constant, the rotation vibration coupling constant, and the centrifugal distortion constant, and it'll give you the uncertainties for those. Alpha E and SDE. This is the thing that you're really wanting out of that regression analysis. It's an analysis of variance, and it'll tell you how sure you are about each of those values. This is where you get 95% confidence intervals on your bond length. So you've got the rotational constant here, and you're going to turn that into the bond length, okay? And you've got your uncertainty here, and we're going to introduce propagation of uncertainty, and we're going to get our uncertainty for the bond length. And so you'll see how sure you are in angstroms of that bond length. And you should have uncertainty in like the 4th decimal place of bond length if you did your assignment correctly. You're going to use the vibrational frequency, and you're going to calculate the force constant. Okay. And you're going to use the uncertainty in your vibrational frequency to calculate the uncertainty in your force constant. And so in this lab, you're going to produce all of these values on this sheet. And it's going to be fantastic. Because you're just taking a spectrum and you're learning how close the carbon and oxygen atoms are to each other. There's no way you could get a ruler to do that. There's no measurement device that we could use to measure the bond length of a molecule except spectroscopy. And so that's what this whole course is about, is using spectroscopy to learn something about nature. And we really depend upon symmetry to simplify things. That's where these J plus or minus 2 and J plus or minus 1 selection rules came from, was symmetry. And then here's just more about that lab. So, yes?
And you said right now you haven't been recording any of this?
I have. No, I split the video.
Okay.
So the second video then will be posted 2 places. It'll be posted in this week's lecture notes, and then also in a couple of weeks when we're doing that lab, I'll repost this video there too. All right. Y'all have a great day.